Welcome to this instructional animation on how an AC generator works. In this video, we'll explore the principles of electromagnetic induction and how the motion of a rotor within a magnetic field generates alternating current. We'll break down the key components of our generator, including the armature, field, slip rings, and brushes, and see how they work together to produce electricity. By the end of this video, you'll have a clear understanding of how a simple AC generator powers a circuit and what factors influence its output. Let's dive in. Our generator consists of an armature which conducts the electricity generated. In this generator, the armature is also the rotor, which, as its name implies, rotates to facilitate the relative motion needed for electromagnetic induction to occur. The field consists of a north and south pole, which generates the magnetic field required to induce a voltage in our rotor as it spins. The lines of magnetic flux run from the north to south pole. The slip rings allow the conduction of current from our rotating conductor, or rotor, to our stationary conductors. The brushes establish a physical connection between the rotating and stationary conductors through the slip rings. Finally, the electrons make their way into our circuit. Our simple AC circuit consists of the conductors and a single light bulb, which represents the load in our system. Let's dive deeper into the workings of electromagnetic induction in our AC generator. We'll examine how the rotor's position affects the voltage generated and the brightness of the bulb. At 0 degrees, the rotor's plane is parallel to the magnetic field. Here, the rotor cuts across very few magnetic lines of flux, resulting in minimal voltage and a dim bulb. At 45 degrees, the rotor starts to intersect a larger number of magnetic lines of flux. This increases the voltage, which increases the flow of current, and the bulb is starting to glow. It's important to note that our rotor is paused to demonstrate the workings of electromagnetic induction at key points along the rotation of the rotor. In reality, should the rotor stop moving, there would no longer be relative motion between the field and the armature, and there would no longer be a voltage induced in our rotor. At 90 degrees, the rotor now cuts across the maximum number of flux lines. This induces the largest voltage in our rotor, causing the bulb to shine brightly. This is due to the fact that as our voltage increases with a constant amount of resistance, current flow in our system will also increase, increasing the amount of power the light bulb is using. As we reach 135 degrees, the rotor begins to intersect fewer flux lines, decreasing the voltage and dimming the bulb. At 180 degrees, similar to the 0 degree position, the rotor cuts minimal flux lines. At this point in the rotation, the voltage is 0, and our bulb is no longer emitting light. At 225 degrees, the process repeats, but in reverse polarity, slightly increasing the bulb's brightness as the rotor cuts across a larger number of magnetic lines of flux. At 270 degrees, the rotor again intersects the maximum number of flux lines, leading to peak voltage and a bright light bulb. Approaching 315 degrees, the number of intersected flux lines decreases, dimming the bulb once more. Finally, at 360 degrees, we're back to the starting position, with 0 voltage and a dim light bulb. This cycle repeats with each rotation, demonstrating how the rotor's position, relative to the magnetic field, directly influences the voltage generated and the brightness of our light bulb. Now, let's experiment with the strength of the magnetic field and observe its impact on our generator's output. Initially, our magnetic field is at its regular strength, with a large number of magnetic lines of flux, indicating a strong magnetic field. If we decrease the strength of the magnetic field, we reduce the amount of magnetic lines of flux which our rotor passes through. As a result, the electrical output to our circuit diminishes. Observe how the brightness of our light bulb dims, corresponding to a smaller amount of electricity produced by our generator. If we increase the strength of the magnetic field, we increase the number of magnetic lines of flux which our rotor passes through. This increases the amount of electricity produced by our generator, leading to a very brightly lit light bulb. As you have seen, each 180-degree turn of our rotor results in a change in polarity in our system. This means that the voltage applied to our rotor is opposite to the voltage applied in the previous 180 degrees of rotation. This causes the current to flow in the opposite direction. This change in the direction of our current flow during each half turn of our rotor is what defines alternating current, or AC electricity. The bulb lights up in the same manner during each half rotation. The light bulb doesn't care which way the current is flowing. When current flows through the filaments of the light bulb, it produces light. Power is produced twice during each full rotation of our rotor, resulting in the light bulb lighting up and dimming back down, 2 times during each rotation of the rotor. The alternating nature of the current flow is fundamental to the AC electricity that powers our homes and devices, and, as you can see, is due to the rotation of the rotor in our generator. And that's how an AC generator produces electricity. As we've seen, the rotor's position relative to the magnetic field determines the voltage generated, causing the light bulb to brighten and dim in a continuous cycle. We also explored how the strength of the magnetic field impacts the generator's output and why the current flow changes direction with every half turn of the rotor. Understanding these principles is key to grasping how AC power is generated and used in everyday applications. Thanks for watching, and we hope you enjoyed this exploration of electromagnetic induction.